Hi, everybody. I'm Somit Gupta. I'm a data scientist in the analysis and experimentation team at Microsoft. And I'm here to talk about some common metric interpretation pitfalls that I've compiled with the help of my colleagues in the same team. Before I delve into metric interpretation pitfalls, a quick recap of online controlled experiment setup. So the concept is pretty trivial. Say you have a new feature X that you've developed, and you want to understand whether this will help your customers or not. So in an A/B testing setup, what you would do is you'll take your existing customer base, and you would split that customer base at random into two equal groups. One group is called the control, which gets the existing product or the system as is. And the other group is called treatment, which gets the existing system plus the new feature X. Now you let this setup run for a while. You collect telemetry and data from both the groups. And at the end of the experiment, you analyze, understand which group fared better, treatment or control, with respect to certain key metrics that you care about. In practice, what we have seen while we run more than 1,000 experiments every month is that even after you set up the experiment correctly and there are no bugs in the experiment, the conclusions the experiment owner can end up would be wrong. Specifically, like the conclusion that my feature X is causing a statistically significant impact on a particular metric might be the wrong conclusion that you get. Before I delve into specific pitfalls, I want to briefly talk about metric taxonomy, which helps us detect and prevent a lot of these metric interpretation pitfalls. At Microsoft, whenever we analyze an experiment, we usually compute hundreds of metrics for that experiment. And those metrics have different roles in the analysis of the experiment, which can be categorized into 4 different categories. The first question that you want to answer when you look at the results of your experiment is not whether the treatment one or the control one, is that whether my results are trustworthy or not. And data quality metrics are the ones which help you answer that, whether you can even look at the rest of the metrics in your experiment and make a trustworthy decision or not. And these help a lot in preventing and detecting a lot of pitfalls we'll talk about. After you have established that your data quality is correct, your metrics are trustworthy, then you would want to ask the question whether or not your treatment was successful. And to answer that question, the metric that you usually use is the overall evaluation criteria, or the OEC metric. That is the metric that you're trying to optimize for in your experiment. And usually a product would have a single OEC metric which multiple experiments are trying to improve. And that OEC metric is the one that aligns with long-term goals of your product, because that is actually the touchstone of success of your experiment or your feature, is that you're improving the long-term goals of your business or of your product. But you're not done after that answering just that question. There are a set of metrics that you're not like explicitly optimizing for, but you want to make sure you're not harming them, or you're not doing an unacceptable harm to those metrics. For instance, performance usually falls into that category. So if you develop a new feature X, you might see like a small tax on performance, that your page loads slower because of that. But you want to make sure that there's not an undue harm to performance, because small undue harm to performance can add up and tank the whole product. Those metrics are what we call the guardrail metrics that you would also have in your experiment. And lastly, you'll have a lot of local feature and diagnostic metrics. So these form the bulk of the hundreds of metrics that we compute. And these are metrics which track user behavior at a very detailed level on different parts of your product, like where did user click, what part of the product did user visit, and having breakdowns by various levels and aggregations by various levels. And this rich set of metrics is really helpful in understanding why a particular treatment caused a change in user behavior or failed to cause a change in user behavior at times. So with this, now I want to move on to some and talk about some common metric interpretation pitfalls. We have 12 pitfalls that we mentioned in our paper. I'll go through four of them in this talk, and for each pitfall, we have a real example of an experiment that we ran at Microsoft with a puzzling result, which illustrates that pitfall. And let's begin with the first one. So the first one starts with is an experiment that we did on the MSN homepage. So MSN.com homepage is basically has a list or a collection of article links on the page. And if you click on any of the articles, you basically get navigated to that article page in that same tab. So the experiment that we ran was that in the treatment, there was a one-line JavaScript change that was made that instead of opening the links in the same tab, we open the link in a new tab. So now if you click on an article, homepage remains as is, and the article link opens in a new tab. So so far so good. Everybody understands the experiment? All right, great. When we analyzed the result of this experiment, what we found was that it had a large impact on performance of the homepage. It led to an 8% increase in the time to load the MSN homepage. So such a large impact on performance would usually mean like it's a big ship stopper, like you'd never ship this if you're like slowing down your product by 8%. So this was a cause of concern, but also a cause of like a lot of a puzzle or confusion that why can a one-line JavaScript change cause such an increase in the time to load a page. So when we looked at this metric, we were able to quickly find the reason. The reason was what we refer to as metric level sample ratio mismatch. So usually when you analyze any metric in an experimentation setting, you expect to have equal number of data points in both treatment and control. Here, the number of page loads in treatment were 8.4 million. The number of page loads in control were 9.2 million. So there was a large difference in the number of data points we were getting from treatment and control, which indicated that there was this is not a fair comparison, that we're not comparing comparable populations. So this observed change in the metric might not be due to the treatment effect, but due to a confounding factor, that the treatment, it did not cause a slowdown in the page itself, but it caused the whole population of the page loads to change in the treatment. So what happened is that in control, when you click on an article, you lose the home page, the next article page loads up. And now if you want to go back to the home page, you'll click the back button. In treatment, there is no back button because you open the links in a new tab. So all you can do is close that tab and switch back to your home page tab, right? So in treatment, you don't need to reload the home page again. In control, you'll have a lot of subsequent home page loads. And as you might all know, that the first page load takes much longer than the subsequent page loads, because in the subsequent page load, your browser has already cached a lot of content. So there was a shift in population where in treatment, you're left with the slower page loads, and you eliminated the need for loading the page again, and the faster page loads were eliminated. So it was not that the treatment was causing the page to slow down, it's just that the whole population had shifted, and this was not that big of a concern because this was not a valid comparison at that point. So the lessons we drew from this was that, one, having metric level SRM tests or sample ratio tests is a good data quality metric that we should have for each metric to make sure that those metrics are valid. And two, wherever possible, it's good to have a decomposition of that metric or breakdown of a metric into smaller levels. So here, if we could actually break down the page load time by first page load time and subsequent page load times, we would have found that the first page load time would be balanced in terms of number of samples, and the subsequent page load time would be the metric where we would have had the SRM. So we could have still made some inference about the first page load time, and we could not still make an inference about the subsequent page load times. So moving on, the second example I want to talk about is from the experiment we ran on a Skype app on iOS. So notifications is a good way to increase, to keep your users engaged. And in this experiment, what we did was we were trying to change the protocol that we use for sending notifications down to the client. So we were using the voice over IP protocol because we thought that that would be more reliable to actually send notifications. So we set up this experiment. We ran it on iPhone, on Skype apps on iPhone. But what we saw was that we saw a lot of unexpected but very strong stat sig movement on call quality related metrics. So again, like this was an unintended consequence. We were not hoping or expecting any change in call quality because of the way we send notifications down to the app. So again, having a good set of data quality metrics helped us debug or understand the root cause of this issue pretty quickly. The cause was that there is a telemetry loss bias here. What happens on apps is that apps will collect the telemetry and cache it on the client, and whenever they get a chance or an opportunity, they will send that telemetry to the server where we can actually aggregate it and use it for our experimentation results. When you send a notification to an iPhone, it wakes up your app, and your app is active. And when the notification is sent through a more reliable channel, the app wakes up more often, and it has more chances to send a telemetry signal in treatment versus in control. So the telemetry loss from treatment was less than that in control. So we're getting more data from treatment, which affected a lot of metrics, including call quality metrics. So this was not a causal impact of this treatment. It is just that it impacted something else, the confounding factor being telemetry loss here. So again, some lessons that we drew from this was it's very important to have data quality metrics measuring the client event loss rate. So you can do it commonly in two ways. One is that you can compare it with another source. So if you have the same event being tracked on the server and the client side, you can see what is the difference between the two events. We usually assume that server-side events are fairly lossless. The other way to do it is to have a sequence number on your client events. So if you know that in a sequence you did not get a particular numbers or index numbers, then you know that you're missing those numbers, those events from this sequence. And also, it's generally good to use server-side telemetry whenever possible because it's less lossy, it's more uniform, and it has less tax on the users. The next example I talk about is from MSN again. So MSN homepage has a carousel of images with links to articles on it. And this is one of the major drivers of engagement on the page. And we constantly run experiments to see if we can add more images onto this carousel or remove more images from this carousel to improve user engagement. So in this experiment, what we did was control had 12 slides in the carousel, or as we commonly call it, the info pane. And in the treatment, there were 16 slides in the info pane. So the hypotheses being that this would drive more engagement because we've seen like a lot of competitor websites have like a lot more slides in their info pane. But when we ran this experiment, we ran into a sample ratio mismatch. So this was a user-level sample ratio mismatch rather than just a metric-level sample ratio mismatch. So remember the initial picture I'd shown that we randomly split our users into treatment and control. So when we analyze the results of our experiment, we expect that we will have roughly equal number of users from treatment and control. And we do a statistical test to actually test that. And whenever we see that there is a significant difference between treatment and control, the number of users we found from treatment group and control group, we call that a sample ratio mismatch. And so here what we found was that there were less number of users in treatment than in control, which was very puzzling because we know that by design we assigned equal numbers to treatment and control. So this was interesting, and we had to dig down deep into what might be causing it. We found that usually the reason that this was happening was that for some users, the engagement, their engagement increased so much that our bot filter thought that they're bots. So for usually like a large percentage of your traffic for any website would be bots. And you want to filter out bots from your analysis because you don't want to optimize for bots. You want to optimize for real human beings. And when you do that, you're filtering out a lot of data. And sometimes the treatment itself can influence what data you're filtering out. So here, the lessons we had was that yes, we need to filter out bots, but we should have metrics to measure how much data we filtered out, so that if we ever see that, oh, we are actually filtering out more data or less data from treatment compared to control, we know that that is causing a bias in our metrics. Another example I want to cover is again from MSN homepage. This is one of my personal favorites. In this experiment, let me talk about the control first. On the MSN homepage, on the top, there's a link to the Outlook.com or an Outlook.com button. It's a common habit. Users will open IE homepage. It loads the MSN IE. It loads the MSN homepage, and they click on Outlook.com, and they get navigated to Outlook.com, and they check their mail. So one of the experiments ran was to see if we can actually encourage users to use the Mail app on Windows 10 instead of actually going to a website. So instead of instead of having the Outlook.com button, now you have the Mail app button. So now when the user clicks on it, the home page remains as is, and the Mail app pops up. It opens up as a separate app. So here what we saw was that it worked beyond our expectations. Like app link clicks went up by 29 times. So it could be a reason to celebrate, but this was like way beyond our expectations. This was a cause of concern. Like, do we understand what's happening here? And this is where like having a comprehensive breakdown and different ways to look at the same data point or same signal helps a lot. So what we found was that our hypothesis is that this was actually a cause of likely confusion for users, because they're very similar looking. So when you click on it, you may still expect to go to Outlook.com, and when that doesn't happen, so any reasonable person would do is they'll click again, and then again, and then again, until they figure out that, oh, this is actually doing something different now. So we actually saw we saw a huge increase in number of clicks on this button. But on the first day, it was very large. By the second day, it was already much smaller. And day over day, it was going down. And the proportion of users who ever clicked on this was smaller. So we are getting more clicks from fewer number of users. So here, the lesson we drew is like from Toyman's law, that any figure or metric that looks interesting or different is usually wrong. So it is very important to have multiple data points to kind of confirm your hypotheses and have those diagnostic and feature level metrics that you can actually form a theory of why users are actually doing what you think they are doing. Here, like only this metric moved and nothing else moved to indicate that users were so happy with this change that there was a 29 times increase. In conclusion, we have more. We have 12 pitfalls. We could only talk about 4 due to lack of time here. But I do encourage you to read the paper. They're all very interesting and applicable to everybody. And also, we hope that experimentation systems become smarter to detect these common pitfalls and avoid them. And also, you should have a rich set of metrics to actually detect and avoid them in the first place. And experimenters should have a healthy level of skepticism while viewing the results. It's very neat and clean interface to see the metric moves or not, but you should actually try to dig deeper to understand why this is happening, and do you have enough support or data points to actually conclude what you want to conclude. Thank you.